Tonight, we're going to talk about something that happened at our nearest stellar neighbor, that has astronomers questioning everything they thought they knew about what we can actually see in space. In August 2025, using the James Webb Space Telescope, the most powerful instrument humanity has ever pointed at the stars, they found what they'd been searching for: a planet orbiting Alpha Centauri A. Not just any planet, but a gas giant, roughly the mass of Saturn, circling the nearest sun-like star to our own. This was supposed to be one of the greatest discoveries in human history. A world orbiting our closest stellar neighbor, a planet just over 4 light-years away, close enough that we might actually visit someday. But then, something impossible happened. The planet disappeared. And by the end of tonight, you're going to understand why this discovery and its subsequent vanishing act might be one of the most important astronomical mysteries of our time. What it tells us about how little we actually know about the universe right next door. Before we get started, if you love exploring the depths of space as much as we do, take a second to like the video or subscribe. It's a simple action, but it helps this channel reach more curious minds like yours. Now, let's begin. Let's start with where this story actually begins, because it doesn't start in 2025. It starts billions of years ago, with 3 stars bound together by gravity in a system we call Alpha Centauri. Alpha Centauri is special for one simple reason: it's close. At just over 4.3 light-years away, it's the nearest star system to our Sun. When you look up at the night sky from the southern hemisphere, Alpha Centauri is one of the brightest points of light you'll see. It looks like a single star to the naked eye, but it's actually 3 stars locked in a gravitational dance that's been going on for billions of years. Alpha Centauri A is the largest of the 3, slightly more massive and brighter than our Sun. Alpha Centauri B is somewhat smaller and dimmer, roughly 85% of the Sun's mass. These 2 stars orbit each other in an elliptical path, getting as close as 11 times the distance between Earth and the Sun at their nearest approach, and separating to about 36 times that distance at their farthest. Then there's Proxima Centauri, a tiny red dwarf star that orbits the AB pair at an enormous distance, about 13,000 times the Earth-Sun distance. Proxima is actually the closest of the 3 to us, which is why it carries that name. But for this story, we care about Alpha Centauri A. For decades, astronomers have been obsessed with finding planets around Alpha Centauri. The logic is straightforward. If we're ever going to visit another star system, if we're ever going to send probes or perhaps even colonists to another solar system, Alpha Centauri is the obvious first target. It's close enough that a journey, while still taking decades or centuries with current technology, isn't completely impossible. A probe, traveling at 1% the speed of light, would reach Alpha Centauri in about 430 years. That's a long time. But it's not infinite. We could theoretically launch something and have it arrive within the span of a few human lifetimes. Compare that to other nearby stars. Barnard's star is about 6 light-years away. Wolf 359 is 7.8 light-years away. Every extra light-year adds decades or centuries to the journey time. Alpha Centauri's proximity makes it special, makes it the natural first target for interstellar exploration. But here's the thing about exploring other star systems. You want to know what you're exploring before you go. You want to know if there are planets there, what kinds of planets they are, whether any of them might be capable of supporting life. Sending a probe to a star system only to discover there's nothing interesting there would be a colossal waste of resources and time. So, for the past few decades, astronomers have been trying to answer a fundamental question. Does Alpha Centauri have planets? This question turns out to be incredibly difficult to answer. Finding planets around other stars, exoplanets as they're called, is one of the great challenges of modern astronomy. Planets don't emit their own light. They're tiny compared to stars, and they're drowned out by their parent star's glare. Looking for a planet next to a star is like trying to spot a firefly next to a searchlight. Over the past few decades, astronomers have developed several techniques to find exoplanets. The transit method watches for planets passing in front of stars, causing tiny dips in brightness. The radial velocity method detects the wobble planets create as they orbit their stars. But for Alpha Centauri, neither method works well. The transit method requires perfect alignment we don't have. The radial velocity method struggles because Alpha Centauri is a binary system where both stars orbit each other, creating wobbles that mask any planet signals. There's a third method, though: direct imaging. Instead of detecting a planet indirectly, direct imaging tries to actually photograph the planet itself. This is extraordinarily difficult because planets are billions of times fainter than stars. To make matters worse, the planet sits right next to the star from our perspective, lost in the glare. But technology has advanced dramatically. The James Webb Space Telescope, launched in December 2021, changed everything. JWST observes in infrared light, where planets glow from their own heat, making them easier to detect. It uses coronagraphs, instruments that block out the star's light, like holding up your hand to block the sun, and it operates at extraordinarily cold temperatures in deep space, allowing it to see incredibly faint infrared signals. The combination makes JWST the most powerful planet-hunting instrument ever built. In early 2025, a team of astronomers proposed using JWST to search for planets around Alpha Centauri A. The proximity of Alpha Centauri means any planets there would appear farther from their star than planets around more distant stars, making them easier to detect. The team focused on Alpha Centauri A specifically, being bright and sun-like, the best candidate. The observations took place over several weeks in late spring and early summer of 2025. JWST pointed at Alpha Centauri A, using its coronagraph to block the star's light, while its infrared camera searched for faint companions. The observing program was carefully designed. Multiple images were taken at slightly different orientations, rotating the telescope between exposures. This rotation is crucial for distinguishing real planets from instrumental artifacts. Artifacts, like internal reflections or detector imperfections, stay fixed relative to the telescope's orientation. Real planets, orbiting the star, stay fixed relative to the star. So, when you rotate the telescope, artifacts rotate with it, but planets don't. By taking images at different angles and comparing them, astronomers can separate true celestial objects from false signals created by the telescope itself. The team also took images at multiple infrared wavelengths. JWST's instruments can observe at different wavelengths across the infrared spectrum, and planets have characteristic spectral signatures, patterns of brightness at different wavelengths that depend on their temperature and atmospheric composition. By observing at several wavelengths, the team could test whether the object they were seeing had properties consistent with a planet. Each observation session lasted several hours. The telescope locked onto Alpha Centauri A with incredible precision, keeping the star centered on the coronagraph mask to within a fraction of an arc-second. This pointing stability is achieved through JWST's fine guidance system, a set of sensors that continuously monitor the telescope's pointing and make tiny corrections thousands of times per second. The infrared cameras recorded millions of photons during each exposure, building up detailed images of the region around the star. But most of those photons came from residual starlight that leaked past the coronagraph. Even with the best coronagraph technology, you can't block all the starlight. Some always gets through, creating a glow across the image that makes faint planets harder to see. The data came down to Earth, transmitted from JWST via radio waves to ground stations. The raw data files were enormous, gigabytes of information encoding the position and energy of every detected photon. These files were processed through a series of calibration steps to convert the raw detector readouts into scientifically useful images. The calibration process accounts for instrumental effects like variations in detector sensitivity, optical distortions, and background noise. It's a complex procedure that requires detailed knowledge of how the telescope and instruments work. NASA maintains a calibration pipeline, a software system that automatically processes JWST data. But astronomers often refine this processing further, using custom algorithms tailored to their specific observations. For the Alpha Centauri observations, the calibration was particularly challenging because the star is so bright. Even with the coronagraph, even with the star blocked, Alpha Centauri A is bright enough that scattered light creates a significant background across the entire detector. The team had to carefully model and subtract this background to reveal faint objects that might be hiding in it. And then, in the data, something appeared. After all the calibration, after subtracting the stellar background, after rotating and combining images from different angles, a point of light emerged. Faint, but real. Sitting about 400 million miles from Alpha Centauri A, the initial reaction was cautious excitement. The team had found something, but they needed to verify it wasn't an artifact. They checked everything. They verified the point of light appeared in multiple independent images taken at different times. They confirmed it stayed at a constant position relative to Alpha Centauri A when the telescope rotated, ruling out instrumental artifacts. They checked that it wasn't a background star or galaxy by comparing their images to star catalogs and deep sky surveys. No known object appeared at that location in any previous observations. They analyzed the spectral properties, the brightness at different infrared wavelengths, and found them consistent with a warm gas giant planet. The point of light had properties consistent with a gas giant planet. Its infrared brightness suggested it was warm, heated by residual energy from its formation and possibly by its star. The spectrum, the pattern of brightness at different wavelengths, showed absorption features consistent with atmospheric molecules like methane and water vapor, compounds expected in gas giant atmospheres. The brightness was roughly what you'd expect for a Saturn-mass planet at that distance, assuming it was still warm from formation. Young planets, planets less than 1 billion years old, are significantly warmer than old planets because they're still contracting and releasing gravitational energy. Based on the brightness and spectral properties, the team estimated the planet's mass and temperature. Comparing its brightness to theoretical models of planetary evolution, astronomers estimated its mass at roughly Saturn's mass, about 95 times the mass of Earth. The temperature was harder to pin down precisely, but the infrared brightness suggested something in the range of 500 to 1000 degrees Kelvin. That's hot by human standards, but cool for a gas giant planet. Jupiter's cloud tops are about 125 degrees Kelvin. Saturn's are about 95 degrees Kelvin. But deeper in their atmospheres, both planets are much warmer, with internal temperatures reaching tens of thousands of degrees. The Alpha Centauri planet, if it was real, appeared to be emitting significantly more heat than Jupiter or Saturn do today. This excess emission would be explained if the planet was younger or more massive, still radiating away its formation heat. Saturn is the second largest planet in our solar system, a massive ball of hydrogen and helium wrapped in spectacular rings. The planet itself has no solid surface. If you could descend into Saturn, you'd pass through layers of increasingly dense gas, eventually reaching a state where the gas is compressed so much it behaves like a liquid. Then, deeper still, where the pressure is so extreme that hydrogen becomes metallic, conducting electricity like a metal. At the very center, there might be a core of rock and ice, but we're not sure. The exact internal structure of gas giants remains uncertain, despite decades of study. A Saturn-mass planet orbiting Alpha Centauri A would be similar. A gas giant, with no solid surface, probably with its own ring system, created by collisions among moons or captured debris. It would definitely have moons. Saturn has over 80 confirmed moons, ranging from tiny, irregular, captured asteroids to massive spherical worlds like Titan. Titan is larger than the planet Mercury and has a thick atmosphere, the only moon in the solar system with a substantial atmosphere. Titan's atmosphere is mostly nitrogen, like Earth's, but much thicker, and with a surface pressure about 50% higher than Earth's. The surface temperature on Titan is about 94 degrees Kelvin, cold enough that water ice is as hard as rock and methane exists as a liquid, forming lakes and seas on the surface. Another Saturnian moon, Enceladus, is smaller but equally fascinating. Enceladus has a subsurface ocean of liquid water beneath its icy crust. This ocean erupts in geysers through cracks at the moon's south pole, spraying water ice and organic molecules into space. Some of this material falls back to the surface, but much of it escapes into orbit around Saturn, forming one of the planet's rings. The presence of liquid water, organic molecules, and energy sources on Enceladus makes it one of the most promising places in the solar system to search for life beyond Earth. If the Alpha Centauri planet is real and similar to Saturn, it might have comparable moons, perhaps a large moon with a thick atmosphere like Titan, or an icy moon with a subsurface ocean like Enceladus. These moons would be worlds in their own right, potentially habitable environments, completely different from the planet they orbit, possibly with moons, rings, weather patterns, everything we associate with gas giant planets. The discovery seemed solid. The team ran every check they could think of. They verified that the signal wasn't an instrumental artifact, some glitch in the telescope's systems. They confirmed it wasn't a background star or galaxy masquerading as a planet. They analyzed multiple images taken at different times to verify the object was moving with Alpha Centauri A through space, confirming it was gravitationally bound to the star. Everything checked out. In August 2025, they submitted their findings to a major astronomy journal and simultaneously announced the discovery publicly. The peer review process for astronomy journals typically takes several months. Submitted papers are sent to expert referees who evaluate the methods, check the analysis, and verify the conclusions are supported by the data. For a discovery as significant as a planet around Alpha Centauri A, the review would be particularly thorough. The referees would scrutinize every aspect of the paper, looking for potential errors or alternative explanations. But the team was confident in their work. They'd been careful. They'd run extensive checks, and the signal appeared robust. So, they decided to announce the discovery publicly, even before the peer review was complete. This is increasingly common in astronomy. Major discoveries are often announced via preprint servers and press releases before the formal publication process finishes. The logic is that important results should be shared with the community immediately, not held back for months during review. Other researchers can begin their own follow-up observations right away, and the broader scientific discussion can start sooner. The announcement made headlines worldwide. Planet found around Alpha Centauri, the headlines read. Gas giant orbiting our nearest stellar neighbor discovered. News outlets around the world covered the story, explaining what Alpha Centauri is, why this discovery mattered, what it might mean for future exploration. Everyone agreed this was potentially groundbreaking. A gas giant orbiting Alpha Centauri A, our nearest stellar neighbor. The implications were enormous. If Alpha Centauri A has one planet, it probably has more. Planets form from disks of gas and dust around young stars, and those disks typically produce multiple planets at different distances. Gas giants like this don't form alone. If Alpha Centauri A has a Saturn analog, it might also have rocky inner planets closer to the star, worlds that could potentially harbor life. The habitable zone around Alpha Centauri A extends from about 0.7 to 1.3 astronomical units from the star, roughly the distance range from Venus to Mars in our solar system. Any rocky planet in that zone could have oceans, atmospheres, and possibly life. Space agencies began discussing what a mission to Alpha Centauri might look like. Projects like Breakthrough Starshot, which proposes sending tiny laser-propelled probes at 20% the speed of light, suddenly seemed less like science fiction and more like genuine possibility. If we knew there were worlds at Alpha Centauri worth visiting, it changed everything about how we thought about humanity's future in space. For a few weeks, it seemed like humanity's future as an interstellar species had just become tangible. The Alpha Centauri planet wasn't just a scientific curiosity. It was a potential destination, a place we might actually go someday. Astronomers started planning follow-up observations. They wanted to observe the planet at different points in its orbit, track its motion, measure its properties more precisely. If the planet was in a 2 or 3 year orbit, observing it over several years would allow precise measurement of its orbital parameters. This would constrain the planet's mass more accurately and might reveal additional planets through their gravitational influences on each other. Multiple research groups applied for more JWST observing time. They proposed different observation strategies, different infrared wavelengths, different coronagraph configurations. Some wanted to try spectroscopy, breaking the planet's light into its component wavelengths, to learn about its atmospheric composition in detail. Others wanted to search for moons or rings around the planet. Still others wanted to expand the search, looking for additional planets farther from or closer to the star. JWST's observation schedule is planned months in advance, and competition for time is fierce. Thousands of astronomers around the world submit proposals each year, requesting everything from a few hours to hundreds of hours of telescope time. A committee reviews all proposals and allocates time based on scientific merit. The Alpha Centauri follow-up proposals were given high priority because confirmation of the planet would be scientifically important, and because the discovery was recent and needed verification. And then, the planet vanished. In October 2025, 2 months after the initial announcement, a different team of astronomers requested their own JWST observations of Alpha Centauri A. They wanted to follow up on the discovery, observe the planet at different points in its orbit, measure its properties more precisely. JWST pointed at Alpha Centauri A again, took new images with the same instruments and same techniques. The star was there, bright as always, but the planet was gone. The spot where the gas giant should have been showed nothing. No infrared point of light, no trace of the planet, nothing at all. The team ran every analysis they could think of. They checked their data reduction procedures, verified their calibrations, searched the entire field around the star. Nothing. They published their non-detection in November 2025, careful to note that they weren't claiming the original team had made a mistake. They were simply reporting what they saw, or rather, what they didn't see. The planet that had been there in May and June was gone in October. This sparked a firestorm of discussion in the astronomical community. Social media lit up with debate. Astronomers on Twitter and astronomy forums argued about what might have happened. Some defended the original detection, others questioned it, and many took a wait-and-see approach, acknowledging that more data was needed. The astronomy subreddit had dozens of threads discussing the disappearance. Popular astronomy bloggers wrote detailed posts analyzing the situation. YouTube astronomers made videos explaining the controversy to their audiences. The story had captured public imagination, and people wanted to understand what was happening. How does a Saturn-mass planet disappear? This became the central question driving the debate. Planets don't just vanish. They're massive objects, 95 Earth masses worth of hydrogen and helium held together by gravity. To put that mass in perspective, 95 Earths is about 60,000 trillion kilograms, a mass so enormous that its gravity holds it in a spherical shape and dominates the space around it. Such an object can't simply cease to exist. Nothing short of a catastrophic collision could destroy such a planet, and even then, the debris would be visible for years or decades afterward. When planets collide, which happens rarely but does happen, the results are spectacular and long-lasting. The impact that formed Earth's moon about 4.5 billion years ago involved a Mars-sized object slamming into the young Earth. The collision vaporized huge amounts of rock, creating a debris cloud that orbited Earth and eventually coalesced into the moon. This wasn't a quiet disappearance. It was a violent event that reshaped both bodies and created a new world. If two gas giants collided, the result would be even more dramatic. The hydrogen and helium atmospheres would compress and heat up, potentially triggering fusion reactions like those in stars. The collision would release enormous amounts of energy, glowing brightly across the infrared spectrum. The debris, a mix of gas, dust, and possibly rocky cores from the destroyed planets, would form an expanding cloud visible for centuries. Nothing like this was seen at Alpha Centauri, A. The follow-up observations showed a quiet, unremarkable star with no trace of recent catastrophe. Several hypotheses emerged immediately to explain the disappearance. The astronomical community, when faced with an anomaly like this, does what it always does. It proposes hypotheses, evaluates them against the available evidence, and designs new observations to test them. This is the scientific method in action, and it's messy and argumentative and sometimes takes years to reach resolution, but it works, eventually. The first and most straightforward hypothesis was that the original detection was a false positive. Maybe what the first team saw wasn't a planet at all, but some kind of instrumental artifact or cosmic background object that happened to appear near Alpha Centauri A in the first observations, but not in the follow-up. False positives are a real problem in astronomy, especially when you're searching for faint objects near bright stars. The history of astronomy is littered with detections that didn't hold up under scrutiny. Some turned out to be instrumental artifacts, glitches in detectors or optical systems that created signals that looked like real astronomical objects. Others were background stars or galaxies that happened to appear in the field of view, masquerading as companions to the target star. Still others were real signals misinterpreted as something they weren't. In the early days of pulsar research, newly discovered pulsars were sometimes suspected of being artificial signals from alien civilizations before their natural origin was established. The first pulsar discovery in the 1960s was initially dubbed LGM-1 for Little Green Men, before astronomers realized they were seeing a rapidly rotating neutron star. In exoplanet science, false positives have caused problems before. In the 1980s and early 1990s, several teams announced planet detections that were later retracted. These early claims used the radial velocity method, measuring the wobble of stars as planets orbited them. But stars have their own intrinsic variability, pulsations and surface activity that can mimic the signal from a planet. Several announced planets turned out to be stellar activity masquerading as planetary orbits. The community became more cautious after these false starts, developing stricter standards for what constitutes a confirmed detection. Today, an exoplanet isn't considered confirmed until multiple independent teams have verified it using different methods or different instruments. For direct imaging detections, the standard is that the object must be visible in multiple independent images, must move with the star through space, confirming it's gravitationally bound, and must have properties consistent with a planetary object rather than a background star. The Alpha Centauri detection met these criteria in the original observations, which is why the team felt confident announcing it. But the original team pushed back on the false positive hypothesis. They'd been extremely careful in their analysis. They'd checked for artifacts, verified the object was moving with the star, ruled out background contamination. They'd used standard techniques that had successfully detected planets around other stars. They'd peer-reviewed their own work internally before submitting it, having different team members independently analyze the same data to verify they reached the same conclusions. False positives happen in astronomy, but usually they're caught before publication. The review process, both internal within a research team and external through journal peer review, is designed to catch mistakes and artifacts. Usually, obviously questionable detections are filtered out during this process. The fact that the Alpha Centauri detection made it through to publication suggested the team had done their due diligence. And usually the evidence isn't as strong as it had been for the Alpha Centauri planet. The detection was at a confidence level of about 5 sigma, meaning the probability of it being random noise was less than 1 in a million. That's the standard threshold for claiming a discovery in particle physics, and has become increasingly common in astronomy as well. 5 sigma detections are rarely false positives from pure statistical noise. If the detection was false, it had to be from some systematic effect, some artifact or contamination that wasn't properly accounted for in the analysis. But what kind of artifact could create a point source at exactly the right position, with the right brightness, with spectral properties consistent with a planet, that appears in multiple independent observations at different telescope orientations, but then vanishes in later observations? That's a very specific set of requirements, and it's not obvious what instrumental effect could produce that. A second hypothesis involved orbital mechanics. Perhaps the planet was real, but its orbit was such that it moved behind the star from our perspective during the follow-up observations. If the planet's orbit is tilted relative to our line of sight, it could occasionally pass behind Alpha Centauri A, becoming invisible as the star's glare obscures it. This phenomenon, called an occultation, happens regularly in our solar system. Planets pass behind the Sun from Earth's perspective, disappearing from view for weeks or months. Venus, for example, goes through what's called superior conjunction roughly every 19 months, when it passes on the far side of the Sun from Earth. During superior conjunction, Venus is invisible because it's too close to the Sun in our sky. The Sun's overwhelming brightness makes it impossible to see Venus, even though Venus itself is still perfectly fine and orbiting as usual. Mars also goes through superior conjunctions, and when it does, we lose contact with Mars rovers and orbiters for weeks, because we can't communicate with them when they're behind the Sun. The radio signals we'd send to Mars would have to pass too close to the Sun, where they'd be absorbed and scattered by the Sun's hot corona. Could something similar explain the Alpha Centauri planet's disappearance? If the planet's orbit passed behind the star from our perspective in October 2025, it would have been invisible, even though it was still there. But the math didn't quite work out for this explanation. Orbital mechanics is very well understood. We can predict planetary positions with extraordinary accuracy. Given the separation distance measured in the original observations, about 400 million miles, or roughly 2.7 astronomical units, you can estimate the orbital period using Kepler's third law. Kepler's third law states that the square of a planet's orbital period is proportional to the cube of its average distance from the star. This law, discovered by Johannes Kepler in the 1600s, based on observations of planets in our solar system, applies to all orbiting bodies. For Alpha Centauri A, which has a mass very similar to our Sun, a planet at 2.7 astronomical units would have an orbital period of roughly 3 to 4 years. That's the time it takes to complete one full orbit around the star. In 3 to 4 years, the planet travels a full circle around the star, about 1,700 million miles of circumference. Over the 2 months between the May-June observations and the October follow-up, about 1/18th of an orbital period, the planet would have moved only about 1/18th of the way around its orbit. That's about 20 degrees of orbital motion, a relatively small shift. Unless the orbit was nearly edge-on to our line of sight, meaning we see it almost perfectly from the side, a 20-degree shift wouldn't move the planet behind the star. The original observations showed the planet separated from the star by several hundred milliarc seconds. Even after 20 degrees of orbital motion, the separation would still be large enough that the planet should be visible unless it passed directly behind the star. And for that to happen, the orbit would need to be aligned edge-on to within a few degrees. Orbits don't come preferentially edge-on, from our perspective. They're randomly oriented in space. The probability that any given planetary orbit is aligned nearly edge-on is quite low, maybe a few %. So it's possible, but unlikely, that the orbit happened to be oriented such that the planet disappeared behind the star precisely during the follow-up observations. Even if the orbit was more elliptical, with the planet sometimes much closer to and sometimes much farther from the star, the math still didn't work. Elliptical orbits have different speeds at different points. A planet moves faster when it's closer to the star and slower when it's farther away, following another of Kepler's laws. But even accounting for this, a planet on an elliptical orbit at that separation wouldn't have moved far enough in 2 months to disappear behind the star, unless the orbit was almost perfectly edge-on. The occultation hypothesis required too many coincidences. The orbit would need to be tilted just right. The planet would need to be at just the right point in its orbit during the follow-up observations, and the original observations would need to have caught it at a different phase. Not impossible, but increasingly contrived. A third hypothesis was more exotic and captured people's imaginations precisely because it sounded like science fiction. Perhaps something destroyed or disrupted the planet in the brief time between observations. Planetary collisions are rare, but not impossible. Our solar system's history includes spectacular collisions that shaped the worlds we see today. Earth's moon formed from a giant impact between Earth and a Mars-sized object called Theia about 4.5 billion years ago. Mercury might be the remnant of a larger planet that lost most of its outer layers in a collision. Uranus rotates on its side, tilted 98 degrees relative to its orbital plane, likely due to a massive impact early in its history. But these collisions happened billions of years ago, during the chaotic early days of the solar system, when planets were still forming and migrating. In the early days of a solar system's formation, when planets are still migrating and orbits are unstable, collisions happen relatively frequently. The first few 100 million years of a planetary system's existence are turbulent. Planets interact gravitationally, their orbits shift, and sometimes they collide or are ejected from the system entirely. Computer simulations of planetary system formation show this clearly. You start with a disk of gas and dust around a young star. Small particles stick together, building up larger and larger objects. Eventually, you get planet-sized bodies scattered throughout the disk. But these protoplanets aren't in stable orbits yet. They're still interacting strongly with the gas disk and with each other. Their orbits migrate inward or outward as they exchange angular momentum with the disk. Sometimes two planets' orbits cross, and if that happens, they might collide. The result is either a merger, creating one larger planet, or a catastrophic breakup, scattering debris throughout the system. These simulations show that collisions are common in young systems, but become increasingly rare as the system ages and settles into stability. By the time a system is 1 billion years old, most collisions have already happened. The planets that survive have found stable orbits where they're not strongly interacting with each other. Collisions can still occur. Asteroid impacts are an example, but major planet-planet collisions become exceedingly rare. But Alpha Centauri A is billions of years old, about the same age as our Sun. Current estimates put it at around 4.8 to 6 billion years old. Its planetary system, if it exists, should have settled into stable orbits long ago, perhaps 3 or 4 billion years ago. Any planet that survived this long has demonstrated it's in a stable orbit where collisions with other planets are vanishingly unlikely. A planetary collision, happening precisely in the 2-month window between our first and second observations, would be an extraordinary coincidence. The probability of witnessing such an event is astronomically small, literally. Astronomers can estimate collision rates based on models of planetary system dynamics. For a mature system like Alpha Centauri, major planet-planet collisions should occur perhaps once every billion years or less. The probability of one happening in any given 2-month period is about 1 in 6 billion. Those are lottery-winning odds, except worse. And even if it happened, we'd see the aftermath. A collision between gas giants would create a debris cloud, a glowing mess of hot gas and dust that would be visible for years. The impact would heat the material to thousands of degrees, causing it to radiate intensely in infrared wavelengths, exactly where JWST observes. The debris would gradually expand and cool, but the process takes years or decades, not months. For weeks or months after the collision, the debris field would be one of the brightest infrared sources in the Alpha Centauri system, easily detectable by JWST. The follow-up observations showed nothing of the sort. No debris cloud, no excess infrared emission, no trace of a recent catastrophic event. Alpha Centauri A appeared utterly normal, a quiet, middle-aged star going about its business. Then there's the possibility of instrumental error, not in the sense of a false positive, but in terms of the follow-up observations failing to detect a real planet. Maybe the planet is there, but for some reason, the second observation didn't see it. Telescopes are complex instruments with hundreds of potential failure modes. JWST has thousands of components, any one of which could malfunction or perform suboptimally. Perhaps the coronagraph wasn't aligned perfectly in the follow-up observations. The coronagraph requires incredibly precise alignment to work effectively. The star must be positioned on the coronagraph mask to within a fraction of a pixel, typically a few milliarc seconds. If the pointing is off even slightly, starlight leaks past the mask, increasing the background and making faint planets harder to see. JWST's fine guidance system is supposed to maintain this precision, but if something went wrong during the follow-up observations, if the star drifted off the ideal position, or if the coronagraph mechanism didn't deploy perfectly, the sensitivity could be reduced. Perhaps the planet had cooled slightly between observations. Young planets, those still radiating formation heat can evolve on relatively short timescales. As they cool, they become dimmer, especially in infrared wavelengths. A planet that was just barely detectable in May might have faded below the detection threshold by October if it cooled by even a few tens of degrees. But this seems unlikely. Gas giants don't cool that quickly. Jupiter and Saturn have been cooling for 4.5 billion years and are still warm. They cool gradually over billions of years, not months. A change large enough to make a planet disappear would require something extraordinary, like a sudden change in the atmospheric opacity that blocked infrared radiation. Perhaps the planet was viewed at a different angle in the follow-up observations. Gas giants aren't uniform spheres. They have atmospheric features, storms, bands, zones of different temperatures and compositions. Jupiter's appearance changes depending on which hemisphere you're viewing. The Great Red Spot, a storm larger than Earth, makes Jupiter significantly brighter when it's on the facing hemisphere. If you observe Jupiter from a distant star and happen to catch it when the Great Red Spot was on the far side, invisible from your viewpoint, Jupiter would appear slightly dimmer. But this effect is small, typically a few % change in brightness. Not enough to make a planet completely disappear. You'd need an incredibly extreme atmospheric asymmetry to reduce brightness by a factor of 10 or more, which is what would be required to take a detected planet below the detection threshold. Perhaps some contamination or instrumental drift made the second observation less sensitive. Space telescopes operate in a harsh environment. Cosmic rays, high-energy particles from the sun and deep space, constantly bombard the detectors, creating spurious signals that must be filtered out. Over time, detectors can degrade, accumulating damage from radiation that reduces their sensitivity. Optical surfaces can accumulate contamination, thin films of material that outgas from other parts of the spacecraft and deposit on mirrors and lenses, reducing their reflectivity. These effects are monitored carefully. JWST's health and status are continuously tracked, with regular calibration observations to ensure the instruments are performing as expected. If there had been a significant change in performance between May and October 2025, the JWST team would have noticed and issued an alert. The teams checked for all of this, and the instruments seemed to be working normally. Performance had not degraded noticeably. The sensitivity was consistent with pre-launch predictions and earlier on-orbit measurements. But it's possible something subtle was overlooked. Space telescope operations are complex, and unexpected anomalies do occur. Perhaps there was a brief thermal event that slightly shifted the telescope's alignment. Perhaps a cosmic ray hit during the observation corrupted some of the data in a way that wasn't immediately obvious. Perhaps the data analysis pipeline had a bug that affected only certain types of observations. These possibilities are difficult to rule out completely, which is frustrating but also a reminder of how challenging this work is. The most intriguing hypothesis, the one that kept astronomers up at night discussing possibilities, is that the planet was real, is still there, but has somehow become temporarily invisible. This sounds impossible, like claiming something has vanished into thin air. But there are scenarios, admittedly exotic and unprecedented, where it could happen. One scenario involves dust. Space isn't empty. Even between planets, there's gas and dust, remnants of the disk that formed the planetary system. This material is incredibly sparse, far more tenuous than the best vacuum we can create in laboratories, but it's there. And in some systems, there are regions of higher density, concentrations of dust in rings or clouds. If Alpha Centauri A has a debris disk, a ring of dust and small rocks orbiting the star, similar to our asteroid belt but more extended, the planet could occasionally pass through a particularly dense patch of this material. Debris disks are common around stars. Many nearby stars show evidence of them, detected through the excess infrared light they emit. The dust in these disks, warmed by starlight, glows in infrared wavelengths. Our solar system has its own debris structures. The asteroid belt between Mars and Jupiter contains millions of rocky objects. The Kuiper belt beyond Neptune contains icy bodies and dust. The zodiacal dust cloud, a diffuse disk of fine particles in the inner solar system, is visible from Earth as the zodiacal light, a faint glow along the ecliptic visible in dark skies after sunset or before sunrise. If Alpha Centauri A has similar structures, and if the planet's orbit passes through one of them, dust could temporarily obscure the planet. As the planet passes through a dense region, dust would absorb or scatter its infrared light, making it appear dimmer or even invisible. Then, as the planet continues in its orbit and emerges from the dust cloud, it would reappear. This happens on smaller scales in our solar system. Asteroid impacts on planets kick up dust that can obscure surface features for months. The 1990s impact of comet Shoemaker-Levy, 9 on Jupiter, created dark spots in Jupiter's atmosphere that persisted for months, visible even in amateur telescopes. These spots were debris from the impacts, dust, and altered atmospheric chemistry that temporarily changed Jupiter's appearance. If an entire giant planet passed through a sufficiently dense dust cloud, it might disappear from view temporarily, especially if observed in infrared wavelengths, where dust is particularly effective at blocking light. But this explanation has problems. First, we don't see strong evidence of a dense debris disk around Alpha Centauri A. JWST's observations would have detected it if it were there. A debris disk, dense enough to hide a planet, would produce its own infrared emission, a glow from dust warmed by starlight. This excess emission would show up as an infrared excess around the star. And while some stars do show this, Alpha Centauri A doesn't show a particularly strong signal. Any debris disk it has must be relatively sparse, more like our asteroid belt than the dense, dusty disks seen around some younger stars. Second, even if such a disk exists, the planet would have to be incredibly unlucky to pass through a dust cloud thick enough to hide it entirely during the exact 2 months between observations. Debris disks have structure, with denser regions and sparser regions, but they're not like terrestrial clouds that come and go. The dust distribution is relatively stable over timescales of thousands or millions of years. If the planet's orbit passes through a dense region, it does so every orbit, once every 3 or 4 years. The probability of the planet being in this region during the follow-up observations specifically, while not being there during the initial observations, depends on the size of the dense region relative to the full orbital path. Unless the dense region covers a substantial fraction of the orbit, the odds are poor. Another possibility involves the planet's atmosphere and the complex dynamics of gas giant weather systems. Gas giants like Saturn have complex atmospheres with clouds, storms, and weather patterns that can change on surprisingly short timescales. Our solar system's gas giants provide examples of dramatic atmospheric variability. Jupiter's atmosphere is a chaotic mess of storms, bands, and vortices. The planet's appearance changes noticeably over periods of months or years as storms evolve, bands shift, and the atmospheric circulation reorganizes itself. Jupiter's Great Red Spot, a storm larger than Earth, has been shrinking and changing over the past few decades. Historical observations from the 1800s show it was much larger then, spanning about 24,850 miles across. Today, it's only about 10,000 miles across, less than half its historical size. the shrinkage isn't uniform or steady. Some years the spot shrinks rapidly, other years it stabilizes. The color also varies, sometimes appearing deep brick red, other times fading to a pale salmon color. These changes reflect complex dynamics in Jupiter's atmosphere that we don't fully understand. Saturn has its own atmospheric peculiarities. The planet's north pole features a remarkable hexagonal cloud pattern, a jet stream that forms a perfect six-sided shape surrounding the pole. This hexagon is enormous, about 18,600 miles across, larger than Earth. It was first observed by Voyager spacecraft in the 1980s and has persisted for decades, but it's not unchanging. The hexagon's appearance varies seasonally, as Saturn's 40-year orbit carries it around the Sun. During Saturn's northern hemisphere winter, the pole is in darkness, and the hexagon fades from view in visible light. During summer, when sunlight hits the pole, the hexagon becomes prominent. The color and structure also change, with different levels of atmospheric haze affecting its appearance. Saturn also experiences massive storms called Great White Spots that erupt roughly once every Saturnian year, about every 30 Earth years. These storms appear suddenly, growing to encompass large fractions of the planet's surface, then gradually fade over months. The most recent Great White Spot appeared in December 2010, growing rapidly to encircle Saturn's northern hemisphere. At its peak, it was visible in amateur telescopes from Earth, appearing as a bright white spot against Saturn's normally pale yellow clouds. The storm persisted for months, gradually dissipating by mid-2011. Such storms are driven by convection from Saturn's interior heat. The planet radiates more energy than it receives from the Sun, powered by gravitational contraction and possibly by the separation of helium droplets falling toward the planet's core. This internal heat drives atmospheric convection, creating updrafts that punch through the upper atmosphere and trigger massive storms. These storms redistribute energy and material in the atmosphere, temporarily changing the planet's appearance and infrared brightness. Neptune, the outermost gas giant, shows even more dramatic variability. When Voyager 2 flew past Neptune in the 1980s, it observed a large dark spot in the planet's southern hemisphere, similar to Jupiter's Great Red Spot. This feature, creatively named the Great Dark Spot, was a massive storm system with winds exceeding 1,240 miles per hour. But when the Hubble Space Telescope observed Neptune a few years later, the Great Dark Spot had vanished. It had completely disappeared, dissipated by the turbulent Neptunian atmosphere. Meanwhile, a new dark spot appeared in the northern hemisphere, and it too later vanished. Neptune's atmosphere is constantly changing, with storms appearing and disappearing on timescales of years or even months. The planet's appearance in any given observation depends on which storms happen to be present at that time. Could something similar explain the Alpha Centauri planet's disappearance? Perhaps the planet underwent some kind of dramatic atmospheric change that altered its infrared brightness significantly. Maybe a massive storm erupted between observations, or maybe high-altitude hazes formed that block infrared emission. Gas giant atmospheres are stratified into layers. The deepest layers we can observe are the clouds, condensed droplets, or crystals of various compounds depending on temperature. Jupiter and Saturn have clouds made of ammonia ice in their upper atmospheres, water ice clouds deeper down, and possibly other exotic cloud layers, even deeper, where the temperature and pressure are extreme. Above the cloud layers are hazes, thin aerosols of tiny particles suspended in the atmosphere. These hazes can be made of organic molecules, products of photochemistry, where sunlight breaks apart methane and other compounds, creating complex hydrocarbons that condense into particles. The thickness and distribution of these hazes affects how much light the planet reflects and emits. A thick haze layer can significantly reduce a planet's brightness at certain wavelengths. If the Alpha Centauri planet experienced a sudden increase in haze production, perhaps triggered by a change in upper atmospheric chemistry or dynamics, its infrared brightness could decrease. In extreme cases, if the haze became thick enough, the planet might fade below the detection threshold of JWST. This is more plausible than dust obscuration from an external debris disk, because it requires only changes intrinsic to the planet itself, not lucky timing with respect to external material. But it still requires an extreme change happening in a very short time window, which is unusual. Atmospheric changes on gas giants typically occur gradually over months or years, not weeks. And it raises the question of why such dramatic atmospheric changes would occur. What would trigger a sudden increase in haze production? One possibility is seasonal changes. Planets with tilted rotation axes experience seasons as different hemispheres receive more or less sunlight over the course of their orbits. Earth's seasons are the obvious example. Our rotation axis is tilted 23.5 degrees relative to our orbital plane, which means the northern and southern hemispheres receive different amounts of sunlight at different times of year. This drives our seasonal cycle of summer, fall, winter, spring. Gas giants also have tilted axes and experience seasons, though they're quite different from Earth's. Saturn's axis is tilted 26.7 degrees, similar to Earth's. Saturn's year is about 30 Earth years, so its seasons last about 7.5 Earth years each. During Saturn's winter, one hemisphere is in shadow, receiving no direct sunlight. The atmosphere cools, circulation patterns change, and the appearance of that hemisphere alters significantly. When spring comes and sunlight returns, the atmosphere responds, warming up and reorganizing. These seasonal changes can be dramatic. Observations of Saturn over its 30-year seasonal cycle show significant variations in cloud patterns, storm activity, and overall appearance. If the Alpha Centauri planet has a tilted axis and is currently going through a seasonal transition, atmospheric properties could be changing relatively rapidly. A planet transitioning from winter to spring in one hemisphere might experience increased storm activity as the atmosphere responds to returning sunlight. This could temporarily alter the planet's brightness until the atmosphere settles into its new seasonal state. But even this explanation has challenges. Seasonal changes occur over months or years, not weeks. A change dramatic enough to make a planet disappear in just 2 months would require extraordinarily rapid atmospheric dynamics, faster than we've observed on any solar system gas giant, and seasonal changes are predictable. If the planet's orbit and axis tilt were known, you could predict when seasonal transitions would occur and plan observations accordingly. The original team had no reason to think they were observing during a season transition, so if that's what happened, it was another unlucky coincidence. The atmospheric hypothesis remains intriguing, because it's the only explanation that makes the planet real, while explaining why it might temporarily vanish. If correct, it would teach us something new about gas giant planets, something we haven't seen before in our solar system, because we can observe our planets continuously and in great detail. An exoplanet 4 light-years away, observed only briefly at long intervals, might exhibit behaviors that we'd notice and understand if we could observe continuously, but that appear mysterious when seen in snapshots months apart. Then there's the possibility that involves something even stranger. What if the planet is periodically obscured by something else orbiting Alpha Centauri A? Perhaps there's a second, darker object in the system, maybe a massive clump of dust or a small dim companion that occasionally passes in front of the planet from our viewpoint. When this happens, the planet disappears behind the obscuring object, only to reappear when the object moves out of the way. This scenario is called a transiting obscura. And while rare, examples exist in astronomy. Some variable stars show periodic dimming caused by dust clouds or circumstellar material passing in front of them. If Alpha Centauri A has such material, and if the planet happens to orbit in the same plane, occasional obscuration could occur. But again, the timing would have to be remarkably coincidental for the obscuration to happen precisely during the follow-up observations. The disappearance sparked a third round of observations. In December 2025 and January 2026, multiple teams requested JWST time to observe Alpha Centauri A again. Proposals poured in from astronomers around the world, all wanting to solve the mystery. JWST's time is precious and heavily oversubscribed. Hundreds of teams compete for every hour of observing time, and the Time Allocation Committee has to carefully decide which projects are most scientifically valuable. But the Alpha Centauri situation was unique. A potentially groundbreaking discovery had been called into question, and the only way to resolve it was through more observations. The committee approved several follow-up programs, allocating dozens of hours to re-observe the system. The third round of observations began in late December 2025, about 4 months after the initial detection and 2 months after the non-detection. Multiple teams had requested JWST time, and the telescope's schedule was adjusted to accommodate several different observing programs focused on Alpha Centauri A. This wasn't unprecedented. When significant controversies arise, JWST's Time Allocation Committee can approve directors' discretionary time, observations outside the normal proposal cycle, to address urgent, scientific questions. The Alpha Centauri situation qualified. A potentially major discovery was in doubt, and resolving it quickly served the broader scientific community. JWST pointed at Alpha Centauri A, yet again, using multiple instruments and observation strategies. The teams coordinated their observations to maximize coverage and minimize duplication. Different groups observed at different times, with different infrared wavelengths, and with different coronagraph configurations. Some used the near-infrared camera, or NIRCam, JWST's primary imaging instrument covering wavelengths from about 0.6 to 5 microns. Others used the mid-infrared instrument, MIRI, which observes from 5 to 28 microns at wavelengths where cooler objects emit more strongly. The idea was to build a comprehensive picture of the Alpha Centauri system across the full infrared spectrum. If the planet was there, but had somehow changed properties between observations, multi-wavelength coverage might reveal what had changed. The teams varied their coronagraph settings, using different masks and different blocking strategies. JWST has multiple coronagraph configurations optimized for different situations. Some are designed for very high contrast, blocking starlight extremely effectively, but only working for planets at larger separations from the star. Others sacrifice some contrast for the ability to see closer to the star. By trying different configurations, the teams hoped to ensure they weren't missing the planet due to a suboptimal coronagraph choice. Some observations were taken at different times of day, accounting for thermal variations in the telescope. Although JWST operates in the cold vacuum of space, its temperature isn't perfectly constant. As the telescope orbits Pluto, its orientation relative to the Sun changes slightly, and this can cause small thermal fluctuations that might affect optical performance. These effects are small, but when you're searching for a marginally detectable object, small effects matter. The results came in over several weeks as observations were completed and data was processed. And the results were complicated. In some of the December images, a faint point of light appeared near where the original planet had been detected. The detection was tentative, barely above the noise level, but it was there. The signal appeared in multiple independent images from the same observing session in the right location, moving with the star as expected for a bound companion. But it was dimmer than before, significantly fainter than the original detection. If this was the same planet, it had somehow lost more than half its brightness. That's a dramatic change, one that's difficult to explain with any known physical process, and it wasn't consistently visible across all observations. In other images from the same observing run, taken just hours or days apart, the signal vanished again. The telescope would observe Alpha Centauri A. In the morning, see a faint hint of something, then observe again that evening and see nothing. Different teams analyzing the same data reached different conclusions. Some argued the faint signals were real detections of a variable planet whose brightness was fluctuating for unknown reasons. They pointed to the fact that the detections, when they occurred, were at the right location and had properties broadly consistent with a planet. Others argued the signals were just noise, random fluctuations in the data that happened to appear near the expected planet location due to chance. They noted that the detection significance was much lower than in the original observations, barely reaching the threshold for claiming a detection. Statistical measures like signal-to-noise ratio were marginal, in the range where you expect some fraction of detections to be spurious. Still others suggested the signals might be real, but not from a planet. Perhaps there's some other object or phenomenon at that location producing variable infrared emission, a background variable star, though that would need to be an extraordinary coincidence to appear right where the planet was expected. Or maybe some kind of dust structure in the Alpha Centauri system that glows variably as it rotates or evolves. January's observations showed similar inconsistent results. The MIRI instrument, observing at longer mid-infrared wavelengths, sometimes detected a faint source, sometimes didn't. The position was roughly consistent with the original detection, allowing for the planet's orbital motion over the intervening months, but the brightness varied wildly. One observation showed a source about 30% as bright as the original detection. Another observation 3 days later showed nothing, with an upper limit indicating any source had to be less than 10% of the original brightness. A third observation a week later showed something again, but even fainter and at a position slightly offset from expectations. The pattern made no sense. No known physical object varies in brightness this way, flickering on and off over timescales of days, with changes in intensity by factors of 3 or more. Variable stars exist, and some vary dramatically. Cepheid variables pulsate regularly, changing brightness by factors of 2 or more as they expand and contract. Eclipsing binary stars dim periodically when one star passes in front of the other. Cataclysmic variables can suddenly brighten during nova outbursts, but all these phenomena have characteristic timescales and patterns. Cepheids pulsate regularly, with periods of days to weeks. Eclipsing binaries dim predictably, as their orbital geometry repeats. Novae brighten suddenly, and then fade gradually, over weeks or months. None of them flicker randomly, on and off, over days, like the Alpha Centauri observations seem to show. Planets, meanwhile, don't vary like this at all. They reflect or emit light steadily, with at most small variations due to rotation or atmospheric weather. A planet's brightness might vary by 10 or 20% as different hemispheres with different cloud coverage rotate into view, but not by factors of 3 or 10, and not erratically. The flickering behavior suggested something unusual was happening. But what? By February 2026, teams were analyzing not just the detections, but the non-detections, trying to understand what they revealed. When you don't see something you expect to see, that's information too, It tells you the object, if it exists, must be fainter than a certain limit. By combining all the observations, both detections and non-detections, astronomers could constrain the properties of whatever was at that location. If it was a planet, it had to be capable of varying in brightness by large factors on short timescales. If it was something else, it had to be something we hadn't encountered before. One team proposed that the original detection might have been a transient event, something that glowed brightly for a short time and then faded. Transients are common in astronomy. Supernovae, the explosive deaths of stars, appear suddenly and fade over weeks or months. Gamma-ray bursts, the most energetic explosions in the universe, flash brilliantly and then disappear. Tidal disruption events occur when stars pass too close to black holes and are torn apart, creating a brief flare of emission. But all these transients are extremely energetic and occur at vast distances. A supernova in Alpha Centauri would have been visible to the naked eye, rivaling Venus in brightness. We'd have seen it without telescopes, and it certainly wouldn't have looked like a faint point source near the star. For a transient to appear as a planet-like point source near Alpha Centauri A, visible only to JWST and then fading quickly, would require some new type of phenomenon we've never observed before. Perhaps a collision between smaller bodies, asteroids or comets, creating a temporary cloud of hot debris. But asteroid collisions don't produce month-long glows bright enough to see from 4 light-years away. The total energy would be far too small. By February 2026, the astronomy community was thoroughly divided on what to make of the situation. This behavior is virtually unprecedented in exoplanet science. Planets don't flicker. Stars flicker because they have active surfaces with flares and spots. Asteroids can change brightness as they rotate, presenting different faces to us. But gas giant planets are large, rotating slowly enough that brightness changes should be gradual, and they shouldn't disappear entirely. The flickering behavior suggested something unusual was happening. But what? By February 2026, the astronomy community was thoroughly divided. Some astronomers argued the original detection must have been a false positive, an artifact that happened to look like a planet, and all subsequent observations were just seeing noise. They pointed out that exoplanet detection is hard. False positives do occur, and extraordinary claims require extraordinary evidence. A planet that appears and disappears isn't behaving like any known planet, which suggests it isn't a planet at all. Other astronomers argued the planet is real, and the inconsistent detections indicate something genuinely new and interesting is happening. Maybe there's a physical phenomenon we don't understand, some process that can temporarily hide gas giant planets from view. The flickering could be evidence of this new phenomenon. A third group took a middle position, suggesting that the truth might be more complex. Perhaps there is something at that location, some object or structure, but it's not a simple planet. Maybe it's a planetary collision in progress, or a planet with an unusual ring system, or some kind of dusty substellar object that varies in brightness. As of March 2026, when additional observations were still being scheduled and analyzed, the mystery remained unsolved. The planet that appeared in May 2025 had not been definitively confirmed or definitively ruled out. Multiple teams had now observed Alpha Centauri A with JWST, and the results were maddeningly inconsistent. Some observations showed something, others showed nothing, and nobody could definitively explain why. This situation highlights something fundamental about how science works, especially at the cutting edge of discovery. Science isn't a straightforward march from ignorance to knowledge. It's a messy, iterative process where observations sometimes contradict each other, where initial results need follow-up and verification, and where the answers aren't always clear, even after multiple investigations. The history of astronomy is full of discoveries that were later retracted, and retracted discoveries that were later confirmed. In the 1840s, astronomers announced the discovery of a planet called Vulcan, orbiting inside Mercury's orbit. Several reputable astronomers claimed to have observed it. Decades of observations followed, sometimes showing the planet, sometimes not. Eventually, it became clear Vulcan didn't exist. The observations were misidentifications of stars or instrumental artifacts, combined with wishful thinking. In the 1990s, scientists announced the discovery of fossil evidence for ancient Martian life in a meteorite called ALH 84001. The claim was sensational and made worldwide headlines, but follow-up analysis cast doubt on the findings. Alternative non-biological explanations for the structures in the meteorite were proposed. 28 years later, the scientific community still hasn't reached consensus on whether the meteorite contains evidence of life or not. The Alpha Centauri planet might follow a similar arc. It might eventually be confirmed as real once enough observations accumulate and the flickering behavior is explained. It might be definitively shown to be a false positive once better data reveals the original detection was an artifact. Or it might remain ambiguous, a marginal detection that neither side can definitively prove or disprove, a mystery that lingers in the literature for years. But regardless of how the Alpha Centauri situation resolves, it's already taught us several important lessons about exoplanet detection and the nature of scientific discovery. First, it's shown us that direct imaging of exoplanets, even with JWST, is still incredibly challenging. We're operating at the very edge of what's possible with current technology. The signals are faint, the observations are difficult, and marginal detections can be ambiguous. This doesn't mean direct imaging is useless. Many planets have been successfully imaged and confirmed. But it does mean we need to be careful and humble about claims, especially for nearby stars where stakes are high. Second, it's reminded us that planets can be more complex than our simple models predict. We tend to think of gas giants as stable, predictable objects. They orbit their stars in regular paths. They have constant brightness. They behave according to well-understood physics. But real planets exist in complex environments. They have atmospheres that can change. They orbit in systems with dust and other debris. They interact gravitationally with unseen companions. If the Alpha Centauri planet turns out to be real and is genuinely flickering in brightness, that would tell us something new about gas giant planets, something we haven't seen before. Third, the Alpha Centauri situation has energized the search for planets around our nearest stellar neighbors. Dozens of research groups are now planning or conducting observations of Alpha Centauri with various telescopes. Some are using ground-based instruments with adaptive optics, systems that correct for atmospheric turbulence. Others are proposing new space missions specifically designed to image planets around nearby stars. Even if the original JWST detection doesn't pan out, the attention focused on Alpha Centauri has accelerated efforts to thoroughly characterize the system. Within the next 5 to 10 years, we'll almost certainly know whether Alpha Centauri A has gas giant planets or not. And fourth, the story illustrates how astronomy has changed in the era of social media and rapid communication. 50 years ago, a discovery like this would have been announced in a journal article read by a few thousand specialists. If follow-up observations contradicted the original finding, the retraction would happen quietly within the professional community. The public would never hear about it. Today, discoveries are announced on social media, discussed on astronomy forums, covered by news outlets before the paper is even published. When the follow-up observations showed the planet was missing, that became news too, and the scientific process of claim and counterclaim played out in public view. This has advantages and disadvantages. The advantage is that science becomes more accessible, more transparent. People see how the process really works, how scientists argue and debate and gradually converge on truth. The disadvantage is that preliminary results get treated as definitive findings, and when those results don't hold up, it can create the impression that scientists don't know what they're doing. In reality, this back and forth is exactly what science should look like. Bold claims get made, they get tested rigorously, and the truth emerges from careful analysis. So where does the Alpha Centauri planet stand now? As I'm speaking, the situation is unresolved. The original team stands by their detection, arguing that they saw something real in the May and June 2025 observations. The follow-up team stands by their non-detection, reporting truthfully what they saw or didn't see in October. The third round of observations in December and January showed inconsistent results that both sides interpret differently. More observations are planned for late 2026 and into 2027. Different teams are proposing different observation strategies, trying to catch the planet, if it exists, during moments when it should be visible. Some teams want to observe at different infrared wavelengths where the planet might be brighter. Others want to use spectroscopy, breaking the planet's light into its component colors to learn about its atmosphere and composition. Still others are proposing observations at optical wavelengths, visible light, where the planet would appear very dim, but where background contamination might be easier to rule out. The scientific community is doing what it does best, applying multiple independent methods to a difficult question, gradually accumulating evidence until a clear picture emerges. This process can take years, sometimes decades, but it works. Answers emerge, understanding deepens, mysteries get solved. There's also a broader context to consider here. The search for planets around Alpha Centauri is part of humanity's larger quest to understand our place in the universe. For thousands of years, we wondered if planets existed around other stars. The answer, we now know, is yes. Planets are common, perhaps more common than stars themselves. But knowing that planets exist is different from finding planets around specific stars, especially stars close enough that we might actually visit them someday. Alpha Centauri represents a threshold. If we find planets there, they become the first worlds beyond our solar system that we might realistically explore. Not in our lifetimes, perhaps, but within the lifetimes of civilizations we might build. Projects like Breakthrough Starshot, proposed in 2016, aim to send tiny laser-propelled spacecraft to Alpha Centauri at 20% the speed of light. Such craft could reach the system in about 20 years and beam back pictures and data. But these missions are only worth doing if there's something interesting to see when they arrive. Finding planets around Alpha Centauri changes the calculation. It transforms the system from a target of pure scientific curiosity into a potential destination, a place we might actually go. That's why the August 2025 announcement was so exciting, and why its subsequent complications are so frustrating. We want to know if there are worlds at Alpha Centauri, because knowing that changes how we think about our future in space. The vanishing planet also raises a philosophical question about the nature of discovery. When do we know something? At what point does a detection become a discovery? The original team saw something in their data that looked like a planet. They analyzed it carefully, ruled out obvious false positives, and concluded they'd found a world orbiting Alpha Centauri A. They published their findings and announced them publicly. By most definitions, that constitutes a discovery. But then the planet disappeared. Follow-up observations didn't confirm it. Other teams couldn't reliably see it. Does that mean the discovery wasn't real? Or does it mean the discovery was real, but the object discovered is more complex than initially thought? This isn't just semantic quibbling. The answer affects how we communicate science, how we train young astronomers, how we allocate telescope, time, and research funding. If we say the Alpha Centauri planet was never really discovered because it wasn't confirmed, we're setting a high bar that might discourage researchers from publishing preliminary but exciting results. If we say it was discovered but remains unconfirmed, we're acknowledging that science is a process, not a collection of definitive facts. Most astronomers take the second view. Science is iterative. Initial findings lead to follow-up studies, which lead to refinement of understanding. Some initial findings hold up, others don't, and many fall somewhere in between, requiring years of work to fully clarify. The Alpha Centauri planet falls into that middle category right now. It might turn out to be real, it might turn out to be a false positive, or it might turn out to be something we don't have a category for yet. Whatever the final answer, the journey to get there is part of how science works. Let's talk about what we do know for certain about Alpha Centauri, because there's actually quite a lot. We know the system contains 3 stars, with well-measured masses, orbits, and properties. We know Proxima Centauri, the red dwarf companion, has at least 2 confirmed planets. Proxima b, discovered in 2016, is roughly Earth mass and orbits in Proxima's habitable zone, the region where liquid water could exist on a planet's surface. Proxima c, tentatively detected through radial velocity measurements, is a larger planet farther out. And in 2020, astronomers announced evidence for a third planet, Proxima d, which would be even smaller than Earth. These Proxima planets are real discoveries, confirmed by multiple independent observations. They don't vanish when you look for them again. They've been observed enough times, with enough different methods, that their existence is certain. This makes the Alpha Centauri A situation even more striking. We know planets exist in the Alpha Centauri system because we found them around Proxima. But Proxima is a red dwarf, very different from Alpha Centauri A, which is a sun-like star. Do sun-like stars in the Alpha Centauri system have planets too? That's the question the JWST observations were trying to answer, and the answer remains unclear. We also know, from decades of radial velocity observations, that if Alpha Centauri A has planets, they're not the easy-to-detect kind. There are no hot Jupiters orbiting close to the star, no massive planets with short orbital periods creating obvious wobbles. Any planets around Alpha Centauri A must be either farther out, like the purported Saturn mass planet, or smaller, or both. This makes sense. Alpha Centauri A and B orbit each other relatively closely. Their gravitational dance would disrupt planets that were too far from either star. Computer simulations suggest stable planetary orbits can exist within about 3 astronomical units of Alpha Centauri A. 3 astronomical units is 3 times the Earth-Sun distance, roughly the orbit of the asteroid belt in our solar system. Beyond that distance, the gravitational influence of Alpha Centauri B would destabilize orbits over millions of years. So, if Alpha Centauri A has planets, they're probably confined to a region relatively close to the star by cosmic standards. The purported Saturn mass planet at 400 million miles, about 2.7 astronomical units, sits near the outer edge of this stable zone. It's in a reasonable place for a planet to exist, which is part of why the original detection seemed plausible. The proximity of Alpha Centauri means we can study it in more detail than more distant stars. We can measure its spectrum precisely, track its motion through space, observe it with high spatial resolution. This wealth of data makes Alpha Centauri an ideal target for planet searches, but it also means there's nowhere to hide. If planets exist there, we should be able to find them with current or near-future technology. The fact that the Alpha Centauri A planet has proven so elusive, appearing in some observations but not others, suggests we're right at the edge of detection capability. We're seeing something, but what that something is remains ambiguous. This is actually a common situation in astronomy. When you're pushing the limits of your instruments, trying to detect signals just barely above the noise, you enter a regime where different observations can give different results. Small changes in observing conditions, instrumental performance, or data analysis methods can mean the difference between detecting something and not detecting it. Pulsars, rapidly spinning neutron stars, were initially discovered as strange radio signals that appeared intermittently. Early observers weren't sure if they were real astrophysical sources or just noise. Only after many observations confirmed the signals were real, periodic, and coming from space were pulsars accepted as genuine. The first exoplanet discoveries in the early 1990s faced similar skepticism. When Michel Mayor and Didier Queloz announced the discovery of 51 Pegasi b in the 1990s, many astronomers were doubtful. A gas giant orbiting extremely close to its star, with a 4-day orbital period, seemed impossible. Gas giants form far from stars, where it's cold enough for ice to exist. How could one end up so close? But follow-up observations confirmed the planet was real. And today we know hot Jupiters are common. The Alpha Centauri planet might follow a similar arc, from doubt to acceptance, or it might go the other way, from initial excitement to retraction. Time and more observations will tell. Let's consider what it would mean if the planet turns out to be real. A Saturn-mass gas giant at 2.7 astronomical units from Alpha Centauri A would be fascinating for several reasons. First, it would confirm that the Alpha Centauri system can form gas giants, not just the small rocky worlds we've found around Proxima. This would suggest the system's planet-forming disk was massive and rich enough to create the full range of planet types. Second, a gas giant at that distance might help shepherd and protect inner rocky planets, just as Jupiter does in our solar system. Jupiter's gravity clears out asteroids and comets from certain regions, reducing the bombardment rate on Earth. And Alpha Centauri, a planet in a similar position, could play the same role. Third, the planet itself might have moons. Saturn has over 80 known moons, some of which are large and geologically active. Titan, Saturn's largest moon, has a thick atmosphere and lakes of liquid methane on its surface. Enceladus, another Saturnian moon, has a subsurface ocean that erupts in geysers through cracks in its icy crust. If the Alpha Centauri planet is real and similar to Saturn, it might have comparable moons, potentially habitable worlds in their own right. And fourth, detecting and characterizing a gas giant around Alpha Centauri A would provide crucial data for planning future missions to the system. Knowing the locations and masses of planets helps mission planners design trajectories, choose science targets, and estimate what kinds of observations will be possible. On the other hand, if the planet turns out to be a false positive, that's valuable information too. It would tell us about the limits of direct imaging, about what kinds of artifacts can masquerade as planets, about how careful we need to be when making extraordinary claims. False positives are an essential part of the scientific process. They help define the boundaries between signal and noise, between real detections and wishful thinking. Every false positive teaches us something about our methods and our instruments. There's no shame in making a claim that later turns out to be wrong, as long as the original work was done carefully and in good faith. Science is about testing ideas, and sometimes ideas don't survive testing. That's fine. That's how the process is supposed to work. The Alpha Centauri investigation is ongoing and will likely continue for several more years. Different teams are developing new observation strategies, proposing different instruments and techniques. Some are looking beyond JWST to future space telescopes that might have better sensitivity or different capabilities. NASA's planned Habitable Worlds Observatory, currently in early development, is designed specifically for direct imaging of Earth-like planets around nearby stars. It would have a larger mirror and more advanced coronagraph than JWST, potentially capable of detecting smaller, dimmer planets. If the Alpha Centauri planet is real, but just marginally detectable with current instruments, future telescopes might see it clearly. Ground-based observatories are also improving. New, extremely large telescopes. Telescopes with mirrors 30 or 40 meters across are under construction. The extremely large telescope in Chile, scheduled for completion in the late 2020s, will be the largest optical telescope ever built. Combined with advanced adaptive optics to correct for atmospheric distortion, these ground-based giants might rival or exceed JWST's sensitivity for some observations. And they can observe continuously, every clear night, accumulating far more data than JWST can with its limited and precious observing time. The combination of space-based and ground-based observations will eventually resolve the Alpha Centauri planet question, one way or another. So, what have we learned from the story of the vanishing planet? We've learned that exoplanet detection remains challenging and that even the best instruments have limits. We've learned that scientific claims need verification through independent observations and that preliminary results can be overturned by follow-up data. We've learned that the universe can surprise us, presenting behaviors and phenomena that don't fit our expectations. And we've learned that the search for worlds around our nearest stellar neighbors is not just a scientific endeavor, but a deeply human quest to understand our cosmic context and our potential future. Alpha Centauri sits in the southern sky, visible primarily from the southern hemisphere. If you're in Australia, South Africa, or South America, you can walk outside on a clear night and see it, a bright yellowish point of light. It looks utterly ordinary, indistinguishable from dozens of other bright stars scattered across the heavens. But it's not ordinary. It's special because it's close enough that light from Alpha Centauri reaches us in just over 4 years, close enough that we can study it in detail, close enough that we might, someday, send probes or even humans there. And somewhere in that system, perhaps orbiting Alpha Centauri A, there might be planets. Worlds we've barely glimpsed, worlds that appeared in our telescopes for a moment and then vanished, worlds that might or might not be real. The question of whether those worlds exist is one of the most important in astronomy right now. Not because finding one more exoplanet would be scientifically revolutionary, we found thousands already, but because these would be the closest exoplanets to Earth, the first worlds beyond our solar system that we might actually reach. The story of the Alpha Centauri planet is still being written. More observations are planned. More data will be collected. More papers will be published. In 5 years, we might look back on the August 2025 announcement as the first detection of a planet that's now confirmed and well characterized. Or we might look back on it as a cautionary tale about the dangers of premature announcement, a false positive that taught us valuable lessons about instrumental artifacts and observational biases. Or we might still be debating it, with the evidence remaining stubbornly ambiguous, neither definitively confirming nor refuting the original claim. Whatever happens, the search will continue. Because we need to know what's at Alpha Centauri. We need to know if there are worlds there, what kinds of worlds they are, whether any of them could harbor life. These aren't just academic questions. They're questions about our future, about whether humanity will remain confined to one solar system or spread to the stars, about whether we're alone in the universe or part of a larger community of living worlds. Alpha Centauri is our gateway to answering those questions because it's the nearest place we can look for answers. And, right now, in 2026, we're standing at a threshold. We have the technology to detect planets around nearby stars, to image them directly, to study their properties. But we're only just beginning to use that technology, learning its capabilities and limitations, making discoveries, and occasionally making mistakes. The vanishing planet is part of that learning process, a reminder that the universe doesn't always cooperate with our expectations, that nature is subtle and complex, and that the most interesting questions are often the hardest to answer. Thank you for joining me on this journey through one of astronomy's newest and most puzzling mysteries. The Alpha Centauri planet might be real, or it might be a phantom, a trick of light and noise that fooled us briefly. We don't know yet. But the fact that we can ask the question, that we can point our most powerful telescopes at the nearest sun-like star and search for worlds there, is itself remarkable. A century ago, we didn't know if other stars had planets at all. 50 years ago, we had no way to detect them, even if they existed. 20 years ago, we'd only found a handful, all giant planets orbiting close to their stars. Today, we're imaging gas giants around nearby stars, seeing them directly as points of light in our cameras. And tomorrow, we'll image rocky planets, Earth-like worlds in habitable zones, places where life might exist. That future is coming, sooner than most people realize. The technology exists, or is being built. The only question is what we'll find when we look. Will Alpha Centauri have planets? Will those planets be habitable? Will we find signs of life there? Or anywhere else in our cosmic neighborhood? These questions will be answered in your lifetime, perhaps in the next decade or two. And when they are, when we finally know for certain what worlds orbit our nearest stellar neighbor, it will be one of humanity's greatest discoveries. Whether the August 2025 detection was the first glimpse of those worlds, or a false start on the path to finding them, the destination remains the same. We're going to Alpha Centauri, if not physically, then at least with our telescopes and our instruments and our insatiable curiosity. We're going to see what's there, to image the planets if they exist, to study their atmospheres and surfaces, to search for signs of life. The vanishing planet is just the beginning of that story, the first chapter in a tale that will unfold over decades. And I, for one, can't wait to see how it ends. Good night, and keep looking up at the stars, wondering what's out there, waiting to be discovered.